Week 2, Lesson 2, Long Columns and Euler's Formula. Last lesson, we classified a column by its slenderness. Now we load it. Euler's formula gives the critical load at which a long, slender column buckles, and the surprise is that it depends only on stiffness and geometry, never on how strong the steel is. We'll find the load, the stress that goes with it, and check when Euler is even allowed to apply. Here's the problem. The very same column we classified last lesson. 50 by 100 millimeter steel section, 1.5 meters, fixed at the base, free at the top. We already have its area, its weak axis inertia, and its slenderness of 208, a long column. The one new ingredient is the steel stiffness. Find the load at which it buckles, the stress that goes with it, and confirm Euler is allowed. Concept 1. Euler governs the long column. Nudge a slender column, and it springs back. That straight shape is stable. Raise the load to the critical value, and the straight shape stops being stable. It buckles sideways. The critical load is set by stiffness and geometry, the modulus and the moment of inertia, not by yield strength. Swap in a higher strength steel, and the buckling load doesn't move, because the stiffness is the same. Concept 2. The critical load itself. Euler's load is π²EI over the effective length squared. Stiffness and the weak axis inertia push it up. The effective length pushes it down, and it does so as a square. Double the effective length, and the buckling load drops to 1/4. Two cautions live in the formula. Use the minimum moment of inertia, the weak axis, and square the whole effective length KL together. Concept 3. The same result as a stress. Divide the critical load by the area, and because the radius of gyration squared is inertia over area, the effective slenderness drops straight into the denominator. So the buckling stress is π² over the effective slenderness squared. Notice what's gone. Area and inertia have collapsed into slenderness, and strength never appears. Only stiffness and slenderness set the stress. Setup. 2 checks before any math. 1. It's a long column, a slenderness of 208, is deep in slender territory. So Euler applies, and we'll confirm at the end that the buckling stress lands below yield. 2. Use the weak axis inertia and the fixed free K of 2. The only new number is the steel modulus from the handbook. Everything else carries over from last lesson. Solve. Part 1. The critical load. Effective length is K times L. Drop the stiffness, the weak axis inertia, and the effective length squared into Euler's formula, and the buckling load comes out at about 228 kilonewtons. The unit bookkeeping lands in newtons. Part 2. The stress and the validity check. Divide the load by the area for the buckling stress. Then cross-check straight from slenderness with π² over slenderness squared. Both land on about 46 megapascals. The small gap is just rounding the slenderness to 208. Now the crucial check. That's about 1/5 of steel's yield. The column buckles long before it could yield, so Euler is valid. The answers: critical load about 228 kilonewtons, critical stress about 46 megapascals, and since that's far below yield, Euler holds. It all came from stiffness and geometry, the modulus, the weak axis inertia, and the effective length. Strength never entered the calculation, which is exactly what last lesson's long column call predicted. Traps. 4 quiet ways Euler misleads. 1. Squaring L instead of KL. The K lives inside the square. Miss it, and a cantilever looks 4 times stronger. 2. The wrong inertia. Euler buckles about the weak axis, so use the minimum. 3. Assuming strength helps. The load rides on stiffness, and every steel shares the same modulus. So a stronger alloy buys you nothing against buckling. 4. Using Euler outside its range. It only holds while the buckling stress stays below yield. Past that, the column is intermediate. Quick recall. Critical load is π² over KL squared. The stress is π² over slenderness squared, or just the load over the area. And the gate? Euler is only valid while the buckling stress stays below yield. Golden rule. Minimum inertia, square the whole effective length, and remember Euler is set by stiffness, never strength. Next up, Lesson 3, Intermediate columns. Euler assumes the column stays elastic, but shorten the slenderness and the buckling stress climbs until it would pass yield. And there Euler overpredicts. That middle ground is the intermediate column. Next lesson we'll find the slenderness that divides long from intermediate, and the parabolic formula that takes over when Euler can't. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.